Okay, so the last thing we're going to cover in nodal analysis is what if, again, before I do that, so in nodal analysis, what we're doing is we define all of our nodal voltages. If we have a current that's already defined on a circuit, so let's say we have a current source, whatever current is going into that node is the value of that current source. If we have a resistor on that circuit that has a current defined with a value, again, the current going into that node is that current. If it doesn't have a current defined, but we have nodal voltages, we can easily define the current that's traveling on that branch using the nodal voltage equation, where we say that V initial minus V final over resistance is going to give us the current on that branch, basically. But what if instead of having a current source on the branch, we have a voltage source on the branch? So if we have a voltage source, it doesn't have a current going through it, or not that it doesn't have a current going through it, we can't define the current that goes through it unless the question gives it to us. So in that case, if we have a voltage source between two nodes, we usually define it as a supernode. Now, there's two types of supernodes. There is one supernode that's the simple one, where you have a voltage source where on one end it's connected to ground and on the other end it's connected to a node in the circuit. In that case, such as the one here that you can see, like the 12-volt source, like this one, or also like this one, right? One end of them is connected to ground, the other end is connected to a node on the circuit. Then basically these two sources are going to help me define the value of that nodal voltage. For instance, if I look at the 12, on the negative side it's connected to ground, on the positive side it's connected to V4. So if I were to write the voltage difference between those two nodes, I would write my higher side, which is my V4, minus my lower side, which is 0, is going to be equal to positive, basically the higher side minus the lower side of this voltage source, which is 12. So then because one end of my node is 0, then my V4 would basically be equal to 12. Same thing with the other source. So my higher side in this case is going to be 0, minus my lower side, which is V2, is going to be equal to 6 volts. So then V2 is going to be equal to negative 6 volts. Or another way to look at it, if the positive side is connected to that node, it's going to be positive of that value, so positive 12. But if the negative side is connected to that node, then it's going to be the negative of that value, so negative 6. Good thing about having a voltage source that's between ground and a node is, because it gives you the value of that node, that it saves you from having to write a KCL at that node, because you already know the value of that node. So there's no point in writing a KCL for it to find what its value is. So that's one scenario for supernode. The other scenario for supernode is where you have a voltage source that's connected between two nodes where none of them are ground. In that case, you have to do two things. The first thing is to basically write the nodal equation between those two nodes in terms of the voltage difference with relation to the voltage source in between. So what I'm trying to say is that sounded so complicated. What I'm trying to say is this 12-volt source, the other 12-volt, not the one we talked about, this one, the one I'm highlighting in green, is between two nodes, V1 and V3. None of them are ground. So the first thing I'm going to do for this, whenever you see something like this, go ahead and write the voltage difference. So my higher side, which is V1, minus my lower side, which is V3, is going to be equal to 12. So we're going to keep this equation with us when we're solving this. The other thing you're going to do is treat this whole supernode that's basically has a circle, pink circle around it. You're going to treat that whole thing as one node, and then you're going to write your KCLs off of that node. So all of these arrows that are in red, basically all of them are going to be your KCLs at this node. Basically what we're doing by treating this as a supernode is we're assuming it's just one node. we're solving everything based on one node, but then at the end, we're going to be short by one equation, and then this is where this equation comes into play. And I'll solve an example to kind of show you what I mean, but that's the scenario. If you have, basically we have two types of supernode, one where one end is connected to ground, and the other one where both of the ends are like connected to two nodes where neither of the nodes are ground. Okay, so let's look at this scenario. So we have this circuit. It's asking us to find the nodal voltages. First thing I'm going to see or look at is, do I have any voltage sources that on one end they're connected to a node, on one end they're connected to ground? Yes, I do. It's this one. So I can easily come and say that V4, because the positive side of 15 is connected to V4, is going to be equal to 15 volts. So what that does for me is it saves me from writing one KCL equation, because I already know the value of V4. So now I have to solve for V3, V1, and V2. Another thing I see is that V1 and V2 have a voltage source in between them. So I'm going to treat this whole thing as a supernode. But I'm still going to write the difference equation between those two. So my higher side, which is in this case V2, minus our lower side, which is V1, is going to be equal to 5 volts. Now let's go ahead and write our KCLs. Now, in terms of the KCL, because I'm treating V1 and V2 as one supernode, I'm going to have one equation at my supernode and then one equation at my V3. So KCL at supernode is going to give me, so 1.25 amps is going in. I'm going to define my other currents. So let's say this one's going out, and then this one's also going out. I'm going to define this one this way, and then this one also going out. Okay, so I'm going to have 1.25 equals, because that's going in, equals to the ones that are going out. So I have the one that's going on the 8 ohm. It starts at V1, ends at V3. My resistance is 8 ohms. So it's going to be V1 minus V3 divided by 8 plus. And I have the one that goes through the 20 ohm, starts at V2, ends at V4. Resistance is 20. So it's going to be initial, which is V2, minus V4. Instead of V4, I'm going to put in 15 because we know that value. Divided by 20. Going to give me 0. So that's one KCL. My other KCL, I'm going to do it at V3. So it's going to be 3 currents. So the 1 over the 8 ohm is going in. So I'm going to have V1 minus V3 divided by 8 going in. It's going to be equal to the one on the 40 ohm, which is V3 minus 0 over 40. Plus V3 minus V4 over 12. Okay, so let's look at how many variables I have. Actually, let me write V4 as 15 again, so I don't count that as a variable. Okay, so I have V1, V2, V3. I have 3 variables, but based on however many nodes I had left, I have 2 unknowns. This is where this equation that I wrote here comes into play. So my third equation, so equation 1, equation 2, and then my third equation is going to be V2 minus V1 equals 5. So now that I have those 3 equations, we're going to do the same thing. Make sure we get rid of all of the denominators, write everything in order of V1, V2, V3, make our matrices, and then try to solve for our variables. I'm not going to do the math for you, but I can give you the answer. So in this case, if you finally write let me make some space. Okay, if you finally write the matrix, it's going to be -1, 1, 0, and then 5 to negative 5, and then negative 15, 0, 28 times V1, V2, V3 equals 580, 150. And then if you solve for your V1, V2, V3, then V1, V2, V3 is going to be equal to 22.4, 27.4, and 17.4. So again, you can either do this with algebra or you can use your calculator. Either or works. So that's basically nodal analysis. You have, technically you could say you have 4 scenarios. One where you know the current on the branch, so it's either a current source or it gives you the current. So for your nodal, it's going to be the value of that current that's going in or out. Or you only have a resistor between 2 nodes. In that case, you would just go ahead, do V initial minus V final divided by R. Or you have a voltage source between 2 nodes where one end of that node is ground. Then that voltage source basically gives you the value of one node and you can skip writing a KCL for that node. For last scenario, you have a voltage source between 2 nodes, none of them are ground. In that case, you would have to treat it as a supernode, write your KCL as a supernode, but just remember, you also have to write the difference equation for the nodal voltages at that supernode as well to make up for the missing equation you have based on the number of your variables. So those are the 4 scenarios for KCL. KVL is almost the same thing, kind of has similar scenarios. It's just that instead of applying it at nodes, we apply it in loops, and instead of solving for nodal voltages, we're trying to solve for loop currents. So let's go ahead and look at that. So loop analysis, it's a dual to nodal analysis, as I just mentioned. It's very similar. It's just solving for solving for loop currents instead of nodal voltages. So yeah, that's what you're trying to do here. That doesn't really matter. So let's go ahead and see. So let's say I have this circuit and I'm asked to solve it using loop analysis. So again, as I mentioned, the first thing we want to do in loop analysis is to go ahead and define our currents in our loops. Now, usually the practice is that you define your currents in the clockwise direction. You can either do them all in clockwise, do them all counterclockwise, or if you want to do one clockwise or one counterclockwise. My suggestion is, if you have a current source on a circuit, you might want to choose the direction of that when you're trying to basically define the direction of your current source. And I'll show you one example of that. But I say that because if you have a current source and then you're trying to define a loop current, if they're both in the same direction, you can easily assume that basically they have the same value. But if one is like going counterclockwise on your current, if you your current source, if you follow it, it's going clockwise, then like they're gonna have negative values, and it just makes it basically a source of error for you when you're solving it on an exam or something where you know you have not that much time. You can't really, catch your mistakes, I would say, or basically sometimes we miss some things. So that's why I'm saying if you have a current source on a loop, when you're defining your current in that certain loop, just define your current in the same direction as your current source. Okay, so let's say we have this loop and we're trying to find the current that's going in either of the loops. We define both of them as clockwise. Yes, they're clockwise. So now let's go ahead and write our KVL. So remember, nodal analysis, we always do KCL. Loop analysis, we always do KVL, right? And remember, when I was explaining KVL, I was saying it applies to loops. Same thing here. So basically, loop analysis is using KVL to solve for unknown variables, whereas nodal analysis is using KCL to solve for unknown variables. KCL and nodal deal with nodes, and you're solving for nodal voltages. KVL and loop analysis deal with loops, and you're trying to solve for loop currents. Okay, so we have this circuit. We've already defined our currents. We want to find our loop currents and basically our voltages in our loops. So if I'm writing a KVL for loop 1, if I start at my source, it's going to be negative VS1 plus V1 plus V3 plus V2 equals 0. And then same thing at loop 2. I have negative V3 plus VS2 plus V4 plus V5 equals 0. So I have those two equations. I mean, I don't have any other loops. Yes, I have the big one, but in this case, the currents that I've defined are I1 and I2, right? I didn't define any other currents. So VS and VS1 and VS2, because they're my sources, I'm going to assume that I already know them. So then the only unknowns I have are V1, V2, V3, V4, and V5. Okay. I have 5 unknowns. I have 2 equations. How can I write these such that I have as many unknowns as I have equations? The way you would do that, remember how in nodal analysis we defined all of our unknown currents in terms of the nodal voltages? It's the same concept here, but in terms of currents. Here we're going to write all of our voltages that are unknown in terms of our loop currents. Okay, so I'm going to define V1 in terms of the loop current that I have. V1 is across R1. R1 only belongs to loop 1. So then I can easily define V1 as I1 times R1. Okay. Same thing as, V2. V2 is going to be same thing. It only belongs to loop 1. So and I1 enters on the positive. So it's going to be I1 times R2. And let me do V4 and V5, and then I'll go back to V3 because it's special. So V4, R4 only belongs to loop 2. So it's going to be I2, R2. And then loop V5, it only belongs to loop 2. So it's going to be I2, R5. R3, however, it's the resistance that's shared between 2 loops. If you ever have a resistance that's shared between 2 loops, you have to define its current based on the difference of current between those 2 loops. So what I mean by that is V3 is going to be equal to R3. So let's look at the currents, right? Let's say I was in loop 1 and I was trying to define the voltage drop across R3 in loop 1. In that case, because I was in loop 1 first, or I'm writing the VL for loop 1, then I'm going to write that current difference as I1 minus I2. If I am in loop 2, and I'm trying to, that's 1. If I am in loop 2 and I'm trying to define my V3 in loop 2, I'm going to assume that I2 leads I1 in that case. So it's going to be I2 minus I1. And I'll show you why that's true. So let's look at KVL1. In KVL1, you're going to see that your V3 is positive. In KVL2, your V3 turned negative. It's exactly because of this. Do you see how basically loop 1 and loop 2, in terms of if you flip I1 and I2 so that you will get like the other one, they're negative of each other or the opposite of each other? Same thing here. So another good check to basically do on the test, if you have an element that's shared between 2 loops, once you write the equation for one of the loops, when you want to do it for the other, for that shared element, make sure that you swap your currents. So if for loop 1, you're writing I1 minus I2, and that's always the case. It's always the 1. If you're in 1, it's always 1 minus 2. Then when you go to 2, it's 2 minus 1. Now, also mention this. That subtraction depends on the direction of your currents. What do I mean by that? In this case, on R3, I1 is going down always based on how I've defined it. I2 is always going up. So they're always going opposite each other. But what if I had defined them, and I'm going to use the green to show it. What if I had defined I1 in the same direction, but then I2 this way? In that case, both of them would be going down on R3. So when I'm defining V3, if it's using the green method, right? Using the green method, then it's going to be R3 times, because both of these basically are in the same direction, it's going to be I1 plus I2. So also keep this in mind. If your I1 and I2 are going in the opposite direction, you subtract them. If you define them such that they're both going in the same direction, you add them. Another thing to keep in mind, if you're defining them such that they're going in the same direction, it depends on which side they enter on your resistor if you have a voltage already defined. So in this case, because I already have a voltage defined, right? I didn't define the V3. It was already defined by the question. Had these two been going in the opposite direction, but in the same direction, but like going up, because my V3 now, when they entered on the negative side, it would be negative R3 I1 plus I2. So those are some things to keep in mind where they're doing loop analysis. So yeah, that's basically how we do it. Write your voltages, write your loop currents, define basically your voltages in terms of your loop currents, and then we're going to plug everything into our KVL equation. So let me write that. So for loop 1, it's going to be minus VS1 plus I1 R1 plus I1 R2 plus R3. I'm in 1, so I1 minus I2 equals 0. And then for loop 2, I have VS2 plus I2R4 plus I2R5 plus R3. Because now I'm in 2, it's going to be the opposite. I2 minus I1 equals 0. So now I have two unknowns, I1 and I2. I have two equations. And that's how you would do a loop analysis. So that's my first case, right? Too much zooming out. Okay, so that's my first case. Now let's do it with numbers. So I have 3 loops, obviously, as you can see here. My currents are already defined. And I'm going to go ahead and do loop analysis to find my loop currents, right? So let's go ahead and write our loop equations. For loop 1, the 4K only belongs to loop 1, so it's just going to be 4K times I1 plus 6K times. The 6K is shared between I1 and I3, but because I'm writing the KVL for loop 1, I'm first going to go ahead and see which direction they're going on the 6K. So I1 is going in this direction, I3 is going in this direction, so they're going opposite of each other. And because I'm in loop 1, loop 1 is going to come first, so it's going to be I1 minus I3 plus, I'm going this way, right? I enter the positive side of the voltage source. Because it's a voltage source, I already know its voltage drop. So I don't need to do a Ohm's law to find this voltage, right? I already know its voltage. So it's going to be 6 volts equals 0. So that's 1. For loop 2, I'm going to have 9K times I2 plus, oh, not plus in this case. So in this case, again, I'm coming up. I enter the negative side of the 6 volts, so it's going to be actually minus 6 volts. And then plus 3K And then the 3K is shared between I2 and I3, but because I'm in I2, again, they're going in the opposite direction. Because I'm in I2, I2 is going to come first. So I2 minus I3 equals 0. And then my third equation, the 3K is again shared, but this time because I'm in the loop 3 is going to come first. So I3 minus I2 plus 6K again. I'm in 3, so 3 is going to come first. I3 minus I1. And pay attention to these. This is the opposite of this, and then this is the opposite of that. So the 3K, 6K, and then the 12K only belongs to loop 3. So 12K I3 equals 0. So I have 3 equations. I have 3 unknowns. Now, I can basically, solve for my variables, make my matrices, and I'm done. So that's how I would write. And when I ask you on the test to write the mesh currents, I mean, obviously I don't want you to leave it here. I want you to kind of simplify it. So, you have A I1 plus B I2 plus, C I3 equals D, and then A prime for basically you solve all of your equations. So you have like 3 equations, all of your I1s are together, all of your I2s together, all of our I3s together, and then you just write your matrices. So basically I want you to set everything up, just not solve it for me, if that makes sense. So yeah, that's how I would write like the simple loop analysis. Now, let's see what would happen if we had a current source. So if we have a current source, as I mentioned, usually what I do and what I suggest you do to not make any mistakes, and because I made those too, that's why I'm telling you. If you have a current source, try to define your loop current in the same direction of the current source. Because why? For instance, in this case, I have a 2 milliamp that's going up. The direction of my current, if I follow it, it also comes up on this, so they have the same direction. So then I can easily say that my I1 is equal to 2 milliamps. Now, like voltage sources that were connected to a node on one end and connected to ground on the other end that gave you the voltage of that node, and you could basically skip writing the KCL for that node. Current sources that are on a loop and are only for that loop and not shared between 2 loops also do the same thing for you. So if you have a current source on a loop that's only for that loop, if your current of the loop is defined in that direction, it gives you basically your loop current. And then once you have your loop current, I mean, the whole purpose of doing the loop analysis is to solve for the loop current. So if your current source already gives you the loop current, then you can basically skip writing a KVL for that loop. So in this case, because my current source, the 2 milliamp current source, gives me I1, I can skip writing a KVL for I1, and I just go ahead and do one for I2, or for loop 2. So for loop 2, I'm going to do a KVL. It's going to be 2 times, because I'm in I2, it's going to be I2 minus I1. And I'm writing it this way because obviously they're going in the opposite direction, and also 2K is shared. And then I get to my voltage source again. If it's a voltage source, it's already giving you a voltage drop, so you just put it as is. But in this case, because I'm entering it on the negative side, it's going to be minus 2. And then plus, the 6 is only for loop 2. So it's going to be 6 times I2 equals 0. But in this case, I know what I1 is, so I can just plug it in here. So once I plug that in here, my only unknown would basically be I2. So I would just solve for I2, right? So in that case, you just solve for I2. So it's 2 milliamps, right? So it's going to be 2 I2 minus basically 4 milliamps, if I plug that in there, minus 2 plus 6 I2 equals 0. And this is 2K, I believe. So 2K times 2 milliamps gets rid of that. Yeah, so it's 4. So then I have these two and then these two. So then I'm going to have basically 6 is going to be equal to 8 I2, and then I2 is going to be equal to 6/8 milliamps. That's it. Okay, so let's see what else we have. So like we had supernodes in loop analysis, we kind of have super meshes. Sorry, we have supernodes in nodal analysis. We have super meshes in loop analysis. So what that means is that you have a current source. It's shared between two loops. So you can't basically say what the voltage drop across that current source is unless the question gives it to you, which almost all the time it doesn't. So in that case, you would kind of have to bypass that current source somehow to be able to solve for your circuit. Just like nodal analysis where we did supernode and we kind of connected two loops together, here we're kind of going to do the same thing in a different way. And there's two methods for mesh analysis. I'll show you both of them. There's a method that I prefer, but if you want to choose the other method, that's totally fine with me too. So let's go ahead and do one example so you can kind of see how it's going to work. Oh, I didn't. Okay. I didn't include one, but I'll show you on this one so you can see. Okay. So I'm not going to solve it all the way. I'll just like write the equations for you because that's what matters to me the most. And then you can kind of figure out what I mean by the two methods. So let's go with method 1, which is my favorite method. The first thing I'm going to do is go ahead and see if I have a current source that is shared between my two loops. Yes, I have one, the 4 milliamp. And then I'm going to define an arbitrary voltage source or arbitrary voltage across it. So usually the arrow is the positive, the other end is the negative. So I'm going to do Vx, arbitrary voltage, whatever you want to call it. Okay, so I've defined that. Next thing I'm going to do is define my loop currents. I'm going to do them all clockwise. Again, depends on what you want to do. And in this case, clockwise actually works in my favor because it's in the same direction of my independent source that's on an independent loop, right? Okay, so let's do 1, 2, 3. For my loop 1, if I'm writing my KVL, because loop 1 has a current source that only belongs to that loop and is not shared, then I know that my I1 is equal to 2 milliamps. So knowing that, I don't even have to write a KVL for I1. I'm going to go ahead and move to loop 2. So KVL in loop 2, I enter the voltage source on the negative side, so it's going to be -6 plus. The 1K only belongs to loop 2, so it's going to be 1K times I2. Let me skip, okay, I won't skip it. And then I come down, I enter the positive side of my arbitrary voltage source that I defined. So it's going to be positive Vx. Then I get to this 1K that's shared between loop 2 and 1. But because I'm in loop 2 and the currents are going in the opposite direction, so this one's going this way, this one's going this way, then it's going to be I2, oops, not that color, I2 minus I1 equals 0. So that's that. Let me define which loop this is at. So KVL at 2. And then KVL at loop 3. If I start here, the 2K is shared between loop 1 and 2. So it's going to be 2K I3 minus I1 plus 2K times I3. And this time, when I'm going this way, I enter the -1 from, the current source from the negative side, or the voltage that I arbitrarily defined. So in this time, it's going to be negative Vx equals 0. Now, cool thing I'm going to do, in order to get rid of that extra variable that I defined, the Vx, I'm going to go ahead and combine my two KVLs that I wrote together. So that basically you want to combine the KVLs that have that arbitrary voltage. In this case, I mean, because I only wrote 2, there's only 2. But sometimes you might write 4 and then it's just 2 of them that have that arbitrary voltage. So you just want to add those together to get rid of that arbitrary voltage source. And yeah. And another thing I'll mention, very, very important, if you're using this method, make sure that the currents that you define in your 2 loops that have that arbitrary voltage are opposite. So when you add them, one of them is a negative, one of them is a positive, you can get rid of them. So pay attention to that as well. So I'm gonna add these 2 together, make them one equation. So if I add them together, then I'm gonna have -6 plus 1k I2 plus 1k I2 minus I1 plus 2k I3 minus I1 plus 2k I3 equals 0. So it's as if I got rid of the Vx's, right? Now, I know I1 because I had a current source that solved this for me, so I know this, I know this. I do not know I3 and I do not know I2, but what's misfortunate for me is that I have 2 unknowns, I have 1 equation. My other equation, just like the super node, is going to come from my super mesh situation. So here on this current source, because it's shared between 2 loops, I can write the difference of the 2 loop currents based on the value of that source, right? So looking at here, which loop current is going in the direction of the 4 milli? Is it I3 or I2? In our case, it's I3. So then the 4 milliamp is going to be equal to the current that's going in the same direction as the 4 milliamp, which is I3, minus the one that's going in the opposite, I2. So I'm also going to use this current, this equation as my second equation, and then have it here. So equation 1, then equation 2 is going to be 4 milliamps equals I3 minus I2. Now I have 2 equations, I have 2 unknowns, I3 and I2, and I can solve for my I3 and I2. So it's as easy as that. That's one method, that's method 1. Now, there's another method that you can also use. It's almost the same, but the reason I do not use it is because with this new method that I'm going to show you, it's really hard to keep track of which current belongs to what. So I'm going to erase what I drew on this circuit. So for the second method, again, you're going to define your loop currents. So let's say, I1, I2, I3. Next thing you're going to do, we know that this is our super mesh. So we're going to act as if that wasn't there, right? So if this wasn't there, then that would mean that these 2 loops would become 1 loop, right? But just like the super node, where when I was doing my nodal analysis of the super node, I still kept those nodal voltages the same. I'm still going to do this. I'm still going to keep track of my nodal currents wherever they apply, but I'm just going to write everything in one equation. So for that yellow loop that I just defined, let me copy this again down there. Okay, so for this, for this loop current that I just defined, it's gonna be, let's see, so I'm going in the -6 and then plus 1k. What's the loop that the 1k belongs to? I2 plus I get to 2k because it's as if that current source wasn't there, right? So I get to the 2k. What's the loop that the 2k belongs to? 3, so I3 plus I get to the other 2k that's shared. It's going to be 2k I3 minus I1, and then plus 1k I2 minus I1 equals 0. So now, if you look at this equation, and then I come up and you look at this equation, you're going to see that they're the same equation. So, yes, if you do it this way, you can skip 2 lines of equations, but it's really hard to keep track of which, if, let's say, you were on the test and you actually erased this part as if that wasn't there, just so you can see everything, then it's going to be really hard to keep track of what currents on what element, because you've already erased that. But I mean, here, because I already kept it there in my circuit, it's fine, but sometimes it's going to be hard. So yeah, you write that, and then your second equation, just like above, it comes from the difference between the two currents and your basically super mesh. So then it's going to be I3, which is in the same direction of the 4 milliamp, minus I2. It's going to give me 4 milliamps. So 2 equations, 2 unknowns. And again, I'm assuming I know I1 because of that current source. So those are the 2 methods for super mesh. Okay. Now let's do an example with dependent sources. So what if I have a loop circuit and it has some dependent sources? How would I approach that? So in this case, let's go ahead and look at it. The first thing I want to look at, do I have any loops that have current sources on them? I actually have 2. Because I have 2, I can easily skip doing loop analysis or mesh analysis on those. So for my I1, I already know that it's going to be, because it's in the same direction of the 4 milliamp, it's going to be 4 milliamps. And my I2, it's going to be Vx over 2k. Now, I still have to solve for my Vx and plug it in there, but I don't have to write a KVL for my loop 2. Okay, so I have those. So the only loops I have to write KVLs for are I3 and I4. Let's go ahead and do that. So for my I3, because I'm entering on the negative side, it's going to be negative 1k Ix plus 2k times. 2k is shared between loop 1 and 3, but because I'm in loop 3, it's going to be I3 minus I1 plus 1k. Again, 1k is shared between 3 and 4. It's going to be I3 minus I4 equals 0. And the same thing for loop 4. So KVL. So for loop 4, again, let's start with that 1k. It's going to be 1k. I4 minus I3 plus another 1k. I4 minus I2 plus 12 equals 0. So, I know what I1 is. I know what I2 is, but I know it in terms of a variable. So I have to find basically Vx, and I have to find Ix. So I can have 2 equations, 2 unknowns, right? So let's go ahead and see if we can find Ix. So Ix is the current that's on this 1k. Can I define it in terms of my loop currents? Yes, I can. So Ix is going to be equal to the current that's going in the same direction, which is I4, minus the current that's going in the opposite direction, which is I2. And in this case, if I plug in the value for I2, it's going to be I4 minus Vx over 2k. Can I write what Vx is? Yes, I can. Vx, if I apply Ohm's law, it's going to be 2k times I3 based on the direction of the voltage minus I1. So basically I can write Vx in terms of this, and then if I plug it in there, I already know I1, so then my Ix would be in terms of I3 and I4, which are basically my 2 unknowns that I was trying to solve for. So X will be I4 minus 2k and I3 minus I1, and I already know I1 in terms of value, divided by 2k. So it's basically going to be I4 minus I3 plus I1. So I have I have IX, I have VX, I plug them in here, and then here to basically plug in for I2. That's it. That is basically how you would solve for everything. So if I were actually writing the matrix, and if I solve the algebra, then I would end up with I1 equal to 4, I1 plus I2 minus I3 equal to 0, I2 plus 3I3 minus 2I4 equal to 8, negative I2 minus I3 plus 2I4 equal to negative 12. And if you put this all into a matrix, then you're gonna, obviously, you know I1 is 4, I2 is 0, I3, oh sorry, I2 isn't 0, wrong value. I2 is negative 6, I3 is negative 2, and I4 is negative 10. So that's all that there is to mesh and mesh or loops are the same, and then node analysis. Use KCL for node analysis. You apply it at nodes. You sum up your currents at nodes, but then what you're trying to solve for are nodal voltages. In mesh or loop analysis, you apply it to loops. You use KVL. You try to sum up the voltages in the loops. What you're trying to solve for are your loop currents. As I mentioned before, if you want to take away one thing and only one thing from this class, I would say take away nodal analysis and loop analysis, or KVL and KCL. Because if it's something that is used a lot in the electrical world, it's going to be these two. Nothing is as important as these two. Whether you study electronics, or you study power, or you study satellites, whatever it is that you study, these are going to apply to it. So as I mentioned before, we're going to have our live session soon. So please watch these videos. Please come to me with questions. That's all I want from you. Come to me with questions. And we'll try to do more examples and answer any questions you might have.